last time in this session before the next coffee break. Again, there has been a slight change in program, so I'll go to the next cover. Thank you.
Thank you very much for letting me talk here. I'm going to talk about something we have been working with Usman Faru, Tobias Fritz, and Marco. It's about asymptotic and catalytic matrix majorization. So this is for now a completely classical talk, so no quantum this time. So this is the outline. And first, I'm going to give some preliminaries on statistical experiments and their comparison. And then I'm going to go on building a certain kind of semi-ring. Okay. And then I'm going to explain what these semi-rings are and how they are actually used. I hope my German spelling is correct. I don't speak German. And then I'm going to do our main results on matrix majorization in the asymptotic and catalytic settings. There's some further topics, but I won't have time to discuss those, so I'll let those be. Okay, so now we go on to the preliminaries. So statistical experiments are one of the basic building blocks of statistics, and they are just the collections of probability measures on some typically standard or measurable spaces where we have some fixed kind of a index of parameters at theta. But actually, my emphasis lies on these finite experiments, where this index set is finite, it has p elements, and then the event space is always a finite set. So it means that the probability.
And now in this finite setting, of course, the probability and now the probability measures are probability vectors. And then we can identify this finite experiment with the matrix whose columns are as well. So we have a matrix with p columns. And then already in the 1950s, it has been characterized when the statistical experiment P is more information than statistical experiment Q. It means that there exists a statistical operator, there's a marking kernel that takes the input probability measures to the output. And it says that P majorizes Q. And now, in the finite setting, which is our main interest, this means that there exists a stochastic matrix T, that is its matrix with non-negative entries, and the columns are up to 1. Such that when we multiply it from the left T, we get the experiment T. It is the matrix formulation. And then we can, this was the one-shot case, but then of course we can do the asymptotic case, which is quite obvious. We just have many copies of the experiments, and then we ask if there exists a high number of copies of this majorization happens. And then the finite description of the same thing as the copies. And then there's the catalytic picture, where we have an auxiliary experiment R that catalyzes this majorization. And again, the finite descriptions of this. We just have a program of the target experiment and the auxiliary experiment. And it's well known that catalytic majorization is more general than asymptotic case. And when we have asymptotic majorization, we can build catalysts in a certain way, and actually we will see this form of this special catalyst. So now I go to this semi. First, I'm going to make some definitions that might not seem very relevant, but actually they turn out to be very useful. So I'm going to, for any, so first of all, we fix the number of vectors we have to look at each. So we fix this natural number. And now for any other number, n, we find this set Vn of n times p matrices with non-negative entries whose columns have the same support. And now we take the union of all these lengths and we modify this. Okay, so there are just matrices with non-negative entries where the columns have the same support, and there are p columns, but then the length of the columns. And I define this special element 0 or O, which is like one row where all the elements are 0. And then also this 1 or I, again, where all the elements are 1 and there's one row. And then for any two matrices P and Q of the set, I'm going to define these binary operations, this box plus and box multiplication, where you just take either the direct sums of the columns, the same name, or then the product operations, the columns of the same. And I still denote by this majorization order when we have this stochastic matrix that takes us from P, even though now P and Q don't have to be normalized. And I'm further going to define this similarity of P and Q if P and Q can be obtained from each other by possibly by reordering the rows and then maybe padding the 0 rows. And the thing why I do this is that when you leave these binary operations to the poset, then they become formed. And I'm going to denote by this square bracket P, the equivalence class of P in this similarity. So why do I do all this? The reason is that now we go on to the coset space. So we go to the equivalence classes with respect to this similarity equivalence relation. And then we define 0 and 1 elements as the equivalence classes to these special elements. And then I can define this addition and multiplication by the earlier binary operations. And I'm also lifting the pre-order given by the majorization to the content space by. And this is something called as a pre-order symbol. But then, what are they? And why do I care about this? The reason is that this is actually nothing very new. This pre-order savings happens. It's successfully used in statistics for a long time. And Fritz, our collaborator, earlier proved this what he called Vergleichsstellung correctly in these pre-order savings, and we are going to use these results for this case. But for that, unfortunately, I have to go through some rather technical slides. But I try to be quick and quick. You can always think of the special saving in the background that you can kind of think that the following abstract saving activities. So you might have some individual. Okay. So now in general, a pre-ordered always a commutative semi-ring is essentially a ring without additive inverses. That's roughly what it is. Always but it also has a pre-order. Pre-order is as usual. And now it's such that when we add and multiply the same element on both sides, we call it the inequality effects. So especially this latter one, this multiplicative case, it's kind of because there are no additive inverses, so it kind of makes sense. There are no negative somehow in the so And now there are some additional things that we don't really have together. We have to actually consider semi-domains where there are no zero devices and stuff like this, and also zero-sum things, elements sum to zero equality. The more important thing is this polynomial growth, meaning that there's a special element U, non-zero element, which is called as the power universal, that can be used to reverse the order to elements by multiplying the other element with higher power of this power universal. This definition can be slightly relaxed in our main application. We only need this kind of power universal. And then I'm going to also need this zigzag equivalence relation, which means that there exists a finite sequence of sets, but we have this zigzag relation. And it looks weird, but it's actually in our application very, very natural. I'm also defining for a given periodic scenario the opposite scenario, which is otherwise the same, but the order is just reversed. And then there are four very special semifields, actually semifields, which are the so-called two temporal semifields, R plus and R plus opposite, and then the two tropical semifields, TR plus and TR plus opposite. Of course, the opposite ones are just the reversed original ones, and the R plus is just a non-negative half-line with the natural addition multiplication. And the TR plus is again, as I said, the same, but the sum is replaced by this maximum. These are very sentimental theories of data. And another ingredient we still need are these monotone homomorphisms, which are, as you might imagine, they are just semi-ring homomorphisms, meaning that they are additive and multiplicative. They take the zero element to zero element, unique element to unique element, the two semi-rings, and they preserve the order. And I call such a monotone homomorphism as degenerate if actually your order doesn't really matter. So the being ordered means that they have the same value for two elements. And yet another ingredient are derivations. That is, we have a monotone homomorphisms to R plus. Then we can define the set of derivations at this phi, which are additive maps delta that satisfy this Leibniz rule with respect to the multiplication. That's why they are called derivations. And actually, in this case, we always have phi as degenerate, and delta is additionally monotone with respect to the free order of S and the natural total order of the line. Okay. So now we are finally able to state the general stuff we are going to use for fix, which is quite an eyeful, but that's how it is. So now S is a periodic ring with some additional properties which are important. But the important thing is that it is a polynomial growth with some power universal. And now we assume that there's some natural number D, and this special homomorphism, which is vector valued, takes us from S to RD of positive entries, non-negative entries, where either every entry is zero or every entry is non-zero. Every entry is positive. And we assume that it has a trivial. Moreover, we assume that this kind of sequence of implications that being ordered means that we have the same value, meaning that this is essentially degenerate homomorphism. And having the same value in this homomorphism means that the elements are actually equivalent to this zigzag order. And now we assume that we take two elements x and y, which have the same value in this homomorphism, especially if they are zigzag equivalent. And we also assume that x is a power universal. This assumption can be actually lifted, but for us, we can make it a bit easier. It's actually a power universal. And now, if all the non-degenerate homomorphisms to these special semifields are strictly ordered, and then for these component homomorphisms of these special homomorphisms, we have that all the corresponding derivations are strictly ordered. Then the two elements are actually asymptotically reordered. Moreover, they are also catalytically reordered with this special catalyst, which has this special refinery, which is the one that has appeared. Okay. So I go back to the case of interest to our special semi-ring, matrix majorization semi-ring, and just state some facts that are easy to see. It is a polynomial. And actually, any element which is at the same time finite probabilistic statistical experiment, where all the columns are mutually unequal, is a polynomial. It's quite easy. Moreover, we can define this special homomorphism by taking all the one norms of columns of the matrix as a different split. And this actually satisfies the conditions. And now the component homomorphisms of this special homomorphism, which are just the one norms of the columns, they are the only degenerate homomorphisms. Okay, this is quite easy. And then to identify the homomorphisms and derivations, I'm going to define these three kinds of maps. Actually, let's first look at the final one, this delta gamma k. It actually turns out to be just a weighted sum of the Kullback-like divergences between the fixed column k and all the other columns L. And I'm going to come back to this later, but let's see. Actually, we don't assume that these parameter tuples, alpha, beta, and gamma, are just any vectors of RB, but they're actually restricted to a particular substance. For the alphas, we define this affine plane of RB, which is just the one where all the parameters are one. And then we have this A plus as a subset, where all the elements are non-negative. And then A minus is a union of these, where one of the parameters is strictly positive and then the others are non-positive. And if we actually look at these first maps with these kinds of alphas, then if D is 2, then this is just a thing that is found inside the logarithm, the standard Renyi divergence. So actually, we start to see some connections. For the betas, they lie in this affine plane where all the parameters are 0. And then we have this special subset B minus, which is a union of sets where one of the parameters is positive and then the others are not. It's a bit complicated, but there's going to be a visualization. And now the intersection of these A plus and A minus is actually the set of these corner points, these basis elements of the natural basis phi. And now we can actually characterize the non-degenerate moment of homomorphisms and derivations of plus. So for the R plus, there are just these F alphas, where F alphas are in this A minus with the exclusion of the polymorphs. And in the opposite case, there are again these F alphas, but now we are in A plus. And then these tropical ones are given by these FT betas, where beta is a non-zero set element of the B minus. And there are no non-degenerate homomorphisms at all in the opposite, tropical opposite case. And then we have the special degenerate homomorphisms given by these component homomorphisms. And then all the derivations with respect to this fixed parameter k are these delta gamma with positive gamma or non-negative. There are some minor things that we take into account. I won't go into the proof, but it's kind of straightforward. The derivation is a bit more involved. I can ask some questions. But now I go to actually the results we have. One thing to note is that when we apply the classical results, depending on whether we are in the original one of these R plus or R plus opposite or T R plus or T R plus opposite, the direction of the inequalities change because of probability. So we can reorder the inequalities by going on to these divergences, ER and ER, which are just as in the range divergence, we just take the logarithm and divide with a suitable prefactor to realign the inequalities. Okay. But a visualization of this in the D equals 3 case is that now we are looking at in the affine plane A, which is now two-dimensional plane, where we have these corner points, these basis vectors, E2, E1, E2, and now the allowed area is this red area. This probability sigma is just A plus, and then the A minus area is just this areas that emerge from the corner points. I'm going to be. And if you look at this with a fixed matrix T, we look at the value of these divergences along this line. It actually turns out that somewhere around here it starts to become increasing. Moreover, we can look at the limits at this corner point and at the infinity. And it turns out that it's nothing else, it's just in the corner point, we get just the derivation, which is determined by the directional angle at which we approach this corner point. And then at the infinity is again this tropical divergence determined by the direction. So it's quite a unique image. So now I come to maybe our main result, which follows now directly from the question. Now we have two finite statistical experiments where we have a common support separately both matrices. Now, if we have strict ordering of all these maps, these temperate and tropical divergences, and all of these Kullback-Leibler divergences of any pairs of columns, then we have asymptotic ordering, asymptotic changes, so that for any sufficiently large n, we have this stochastic vector Cn that takes us from pk as n to qk as n. It's a very straightforward. And then again, we can have the same asymptotic catalytic result with these special catalysts that arise just from the theory, which has had this binary. And actually, this theorem solves a conjecture posed by Wu and others earlier, where they looked at the D equals 2 case, and they posed the general D case as a conjecture. And this theorem is roughly a positive answer. There are some differences in these kind of infinity conditions, these tropical conditions, but I rather think that our form measure is correct. We need all these tropical conditions. They have size. Okay. So the final result I'm going to present is that we are now in the fixed probability space with fixed size. And then we have full support statistical experiments with this fixed depth, such that this P experiment is such that any two columns, non-equal columns, are non-equal. And now it turns out that we can have actually if and only conditions for this kind of approximate catalytic majorization. It means that for any positive epsilon, we have a basically a statistical experiment Q epsilon which is epsilon close to the target. And then we have this epsilon catalyst that catalyzes this matrix majorization for P, and then this approximate QX for any. And this is equivalent to having these non-strict inequalities involving all these temporal divergences. And actually, we can even fix that in this approximate target Q epsilons. It is just such that actually the kth column is just the kth target for a fixed k. We can do this if you want. But I won't again go to the proof because I think I don't have. And there were some further topics about simple majorization, but these topics are rather, can maybe have a quick look. There are some results that have been proven earlier about this simple majorization probability vectors by Timesh and Jensen, involving just traditional Rayleigh divergences or Rayleigh entropy. And actually, it can be new proofs for these results using these similar methods. Also, there's a result due to Ohan and Nikita about kind of an approximate version of these results, and we can also give quite a nice proof for this using the same version. But that was pretty much it. Yeah, maybe the remaining questions are the more interesting ones. There's a possibility that we can actually lift this condition of the common support of the columns. We are currently looking into this and see promising. And another big question is about the quantum extension of these multi-part divergences. And also the application of these stuff to for example, tables is equal to Thank you.
Thanks. Question?
Yes. The zero result means that exact process and like exact asymptotic.
Sorry, can you repeat?
The zero result in the exact process and exact asymptotic transformation is equivalent. It's given.
No, in general, the catalytic one is always. It seems to be well. I think there are other examples. Catalytic ordering is more general. You need less things for catalysis than for asymptotic.
And just the satisfactory curiosity. It's an application in mind, or it's just you're the same.
I think this is kind of one of those because this is what we were looking more about these simple majorization stuff, but he prompted us to do the and it's more interesting because these are more and actually it turns out that matrix majorization is in some sense in my opinion even easier than simple mathematically it's somehow.
When you had questions satisfying curiosity,
Do you have some replays? Possible to present everything.
Do you have other applications in mind for this, like probability semi-ring these concepts? I think it's like an interesting concept, but I mean, it's not so clear what you use it for, right?
There are many, for example, these existing, like how I define the semi-ring is like it's applicable to this, especially to this exact majorization. So we don't allow any errors, although we have the one asymptotic result. But there are these other kinds of like Strassen pre-orders, like in the simple majorization, there's something called as sub-majorization, which doesn't really have, in my opinion, very clear interpretation like what it actually means, but it is a very good tool For example, this overall magnetic result, I quickly mentioned here, even they use this kind of submajorization order to prove the result. And the submajorization order is particularly nice order. It has these Russell special properties, which make it very kind of easy to handle, although on its own it doesn't have much meaning except as a tool for proving this kind of approximate.
If you found a nice figuring of channels, you can use your channels.
I kind of toyed with the idea, but many of the conditions become hard. I think that, for example, the polynomial growths may be okay, but in the quantum case, the problem is always, in the classical case, you can quite easily characterize all the monotone homomorphisms derivations, because the classical case is so nice because everything decomposes because of the classical structure. But in quantum case, we cannot decompose, for example, states or channels. We cannot use the additive structures to kind of break down them. So the characterization becomes difficult. But in like abstract sense, the Fair-Gleichstein says it says that if we manage to identify all of these maps, then they characterize this orderings. But then we are not really able to actually identify what all of these maps are. So that's the problem.
Good. Yeah, so maybe we should move on to the coffee break. So let's take speeches again.